Anybody got any questions before class?
Yeah, very last part of the report, how do you combine? So it's, I know you probably don't know, because I don't remember the last question. It's the integral of the direct delta of AX.
It's because this one.
So there are history classes.
Yeah. So I think I understand how I supposed to. Okay. So we should change the variable. Like y equals
The previous problem. Well, because the answer to this problem is
So.
like this.
Assuming that is
So for the start, you have to
Oh, really? Oh, man, that's okay. That's a mid assumption. That makes sense. Step one.
It's also.
And as hard as it could.
Sure, I got that. So when it's negative, it
That's so.
really. It's negative.
because if A is negative, then dx is dx
That's
positive.
your
y is
part.
negative.
Right.
Look here, A is negative,
I'm too short.
x positive corresponds to negative y.
Whoa.
Goes from plus to minus.
I know a lot of.
That's negative. So you get 1 over to go on negative 1.
Oh, no, that's not.
Why is it? Why?
Because this is the derivative.
Yeah.
So we had a question about the last question on the homework related to direct delta functions. We have the delta function of a constant times x. And this is going to be equal to 1 over the absolute value of a times the function evaluated at 0. The way to tackle that is to assume either a is positive or a is negative. And, so if you assume that a is positive, then it's easy just to do a change of variables. Take x is equal to y over a, and then dx is 1 over a times dy. And so you get a factor of 1 over a out here on that. And then this integral looks like the one that you've done before, the delta function. So it's 1 over a times f of 0. So let's suppose that a is negative. If a is negative, you have to be a little careful here, because if a is negative and x is, say, positive, right? Y is equal to ax. So at the limit of integration here, where x is going to negative infinity, y is going to be positive. So you have to, the limits of integration have switched. Like this. See why? Because if a is negative, then this lower limit for x of going to negative infinity corresponds to a positive infinity for y. So you change the variable, you also have to change the limits. These are the limits for y. Right? You see that? Okay, so now in order to switch it back to this form, we have to flip the limits here, so you get a negative sign. So that negative sign there, so now we get this is negative 1 over a times f of 0. So if a is positive, you just get a 1 over a. If a is negative, you get negative 1 over a. Combine those two together by just taking the absolute value, right? Negative 1 over a is positive. Negative. So you can combine these two as 1 over the absolute value of a.
Will you please explain why you combine 1 over a and 1 over negative a, or negative 1 over a instead of being 1 over absolute value of a?
Yeah, absolute value of a is a if A is positive, it's negative A if A is negative.
How did that do?
What's the absolute value of function? If it's 1 greater than 0, then the absolute value of 1 is 1. If 1 is less than, if you have negative 1, then the absolute value of negative 1 is negative 1, negative of negative 1. Right? Absolute value of negative 1 is the negative of negative 1. 1.
How is it a negative?
Right. The negative of negative is a positive. The absolute value is always positive.
How did you obtain that additional negative there?
It's just the definition of the absolute value. You take away the sign. Right?
Exactly. I thought that just means.
So if A is negative, I'm going to multiply it by another negative to make it positive.
But so wouldn't it just be both?
We're getting, I'll talk about it after class. I think you're making it hard. So you can combine 1 over absolute value of A is always positive, whether A is negative or positive. Right? So that combines both of these. This is positive, this is positive, this is always positive.
So Dr. Duff,
Yes.
so with the definition of the absolute value that you just said, so the absolute value bars were inside would be -1, meaning that it's negative of a -1.
Yeah.
So if you were to put a positive number, wouldn't you get a negative number out with that definition?
No. Absolute value of A is just A if A is positive, but it's negative of A if A is negative.
Okay, just use whichever one for whichever value of A you have.
Yeah.
Okay.
Right.
Okay. I was more referring to the one they use for negative. Okay, yeah, that makes sense.
As an example, the absolute value of -1. Okay, so which -1 here, A is negative, so use this one.
Mhm.
So it's the negative of -1, which is +1.
Right.
Absolute value of 1, you use the upper one, since 1 is positive, it's just 1.
Okay.
Okay. Let's talk a little more broadly about something. Before we get, I'm going to cover prepare you for the homework on Monday. But I wanted to talk about something a little bit more general about the subject of quantum mechanics and physics. Because quantum mechanics is an area which has a lot of confusion in it. And it's presented a problem for physicists, but some of the problems, they're kind of interesting. So I'm going to take a step back and try to talk generally about what physics is about and what quantum mechanics is about generally. In fact, I'm going to take a step even farther back. What does science mean to us? So you think about an animal like a cheetah. Cheetah, everybody knows, I think, has seen films of a cheetah moving very fast, right? They're very fast for a short time. They can go up to 60, 70 miles an hour, something like that, for just a few seconds. But it's enough for them to catch prey. A hawk has really exquisite eyesight, or an owl. Really fantastic eyesight. They can spot prey from great distances. A bat. Have you watched bats? We have bats around here. They're really cool. You go out about sunset. If you haven't seen this, you should go out. Just about anywhere. Just go out, stand up. Don't be under trees. Get where you can see the open sky. When you look up, it's got to be still a little bit of light in the sky. You'll see the bats flying around, catching bugs. They're flying around about 10, 20 feet up. They're zipping all over the place. They fly very erratic. Catch this bug and then they'll zip over here. They're using sonar. Just figure out where the bugs are. It's really cool. If you haven't seen it, you really need to. That's easy to see because they're all over the place here. They just eat bugs. They won't hurt you. Okay. So you can see in each of these cases, you could express this as the cheetah is built for speed, and the owl is built for visually finding prey. My dog, when I come home, my dog examines. She smells me all over the place, and I'm often wondering what exactly is she figuring out. You know, all these interesting smells I'm bringing home. What does she make of these things? It's kind of interesting. What are we made for? We don't have particularly good smell or eyesight. We're not that fast. We don't have particularly good hearing. There's always some other animal that's better at something, except for one thing. What is that? Our minds. What is our mind made for? Are we made for? What does the mind seek?
To express ideas.
Say again?
To like express ideas.
Even before you express them, you want to know them. And what are the ideas? What are the ideas? You want to know. The mind seeks knowledge. The mind seeks to understand. So you could say we are made to know. Or like even better, because you might even think you know something, but it's wrong. We are made to really to know the truth. So I like it even better to say we are made for truth. But what is truth? What do you know? You know the things around you, right? We were talking earlier this semester that what you know first and best is stuff, common, ordinary, everyday things around you. You know the people, you know bats, you know dogs, you know things around you. And so our ideas about those things are true or false, depending on how well they conform to those things. So the truth is in our minds is judged by those things, how well we know those things. The truth in our minds is conformity of our ideas to reality. Science is so important to us because it's a way for us to understand those things around us. It helps us to be certain about those things, to come to the truth, which is what we're made for. This is core, central to our being, to know reality. That's why science is so important. So science presumes, and you discover really, that the world is orderly, that there's things that make sense out there. So there is an objective reality independent of us. And we can know it. We can know that reality. Science is objective. Objective knowledge of those things, objective things around us. That's why it's so important, because it goes to the core of our being. It's important for everybody to understand science, at least in some way. Even if they're not in an advanced science course, they need to understand in some way, especially how modern science works. At least in some way. Right? They're not going to understand the details. They're not going to be able to sit through solutions to Schrodinger's equation. But they need to understand basically what math is about, and how modern science relies on math, how it helps us to come to understand objective reality. So I was having a conversation, I was giving a talk a couple weeks ago, and it was about quantum mechanics, actually, to a bunch of other physicists and people doing quantum information, quantum computing, giving a talk about the nature of quantum mechanics. And I was going along, and I said a few things, and in the middle of the talk, one of the guys, one of the professors in the talk, wait, no, that's wrong. That's not right. So it spawned a discussion, And that kept going after the colloquium. Right after the talk was done, I tried to answer his question, but he wasn't satisfied. After the talk, we kept talking. This went on for a week. We were talking to each other every day for a week. And we had these long, protracted discussions. Come to my office, I go to his office. We exchanged emails. And finally, at the end of the week, he said, "Oh, I get it." So I said, "Okay, let me make sure I understand this. But what you said was false, and what I said was true, right?" And he said, "Yeah." And then he said, "Thank you." See, that's a guy you can deal with, and he cares. He wants to understand. And when he came to the truth about something, he realized he was wrong, and that I had shown him the truth. And he considered it a kindness that I had actually corrected his error. That's an attitude that when I was coming up in physics, when I was in the classroom learning physics for the first time and then in grad school, people generally in physics had that attitude that that's a good thing. Because, and in fact, it's kind of funny, people who aren't in physics are kind of struck by how physicists can argue with each other in public, right? And nobody gets his feelings hurt, right? And in fact, you come to the conclusion at the end, wow, I learned something. Thank you very much. It's a kindness. In fact, it's a great kindness. If we're made for truth, then for me to fix an error in your mind and bring you to the truth, that's a great act of kindness. And it's true for somebody to fix an error in my thinking. It's a great act of kindness to do that. It takes a lot of work sometimes. So there was somebody during that week, a friend of mine, who not a physicist, who overheard the conversation on the phone and the other out in the hall. She thought that we were being kind of rude to each other, because we were very engaged in this conversation. And she said, I tried to explain what the conversation was about, but she doesn't have the physics background, so I was trying to do it in general terms. Trying to fix, help him to see that he's wrong. She said, well, you're saying he's got a bad opinion? Your opinion is better than his opinion? And I kept saying, no, physics is not about opinion. It's not about that. And statements can be wrong, and statements can be correct, can be true. And we want to find the truth. And she, after trying to explain that to her for a while, she finally said, oh, you really care about the truth, and you think you can know the truth? That struck her as a strange statement. That I thought I could know the truth, and I could actually demonstrate it logically to somebody else, or by some kind of experiment or something. She had never heard that before. That was really strange. You can know the truth. You think you can know the truth, and you think you can prove it to somebody else? It's a strange idea to her. And actually, I noticed that kind of subjectivism, that you can't really know the truth. The truth is just individual. There's my truth, your truth. Don't try to push your truth onto me, right? Because it's just an opinion. That's pretty widespread these days. I'm finding it, in fact, it's really in the culture. And that this kind of understanding that physics brings us to is countercultural. And it's even in physics these days. There's more and more subjectivism in physics. That same week, somebody else who was in that same talk heard us going together talking about this stuff. He was a professor, physics professor. And he's, I asked him later what he thought about the question that had been raised. He said, well, you've got your opinion, and that other guy's got his opinion. This is a physics professor. Holy cow, what are we talking about here? Don't you think there's a truth to the matter? And he said, well, no, I don't. You've got your opinion. You just kept repeating that, right? And I said, I can prove it to you. I can show you. From basic principles, I can work my way up and demonstrate, as I did with the other professor, But the truth of the matter, couldn't budge it, which struck me as really strange. And I've noticed a lot more of that among physics faculty and students over the years. There's a lot more of that in the physics community than they're used to. When you get into that kind of situation, you ask somebody, why did you say that statement talking about physics? That's kind of like a personal affront. What do you mean? You can't discuss anything. You can't have, because they don't know why they say that. They don't know why they're doing it. It just becomes for them a kind of an opinion. That's all they have. And so when you ask them, why do you have that opinion? That's kind of a personal matter. That's a personal question. It's my own personal belief. They're talking about physics. It's my own personal belief. Don't ask me questions like that. So there was, when I was in grad school, I told you my advisor was Richard Feynman. There was another professor who came to, he was a new professor at Caltech, named was David Politzer. And he had just done a fantastic work relating to what's called asymptotic freedom. It has to do with the strong interaction and the binding of quarks together to form a proton. He's done some really amazing, very interesting work. And Feynman disagreed with it. And they spent, I could see them in the hallway, day after day. Feynman is arguing with Politzer. And they're going on, writing on the board. It's going on for days, weeks it went on. And then one day I was there when Feynman, he just stopped. Politzer had explained something more to him. He stopped. Oh, you're a clever guy. I understand. That's really cool. And then after that, David Politzer got the Nobel Prize. And I think Feynman had something to do with that because he, after arguing with Politzer all this time, he finally understood. And it took Feynman a while to understand what Politzer was telling him. And Feynman was not slow at stuff. It took him a while to get to that. So I just noticed that, that was back then, and that was so typical in the physics community. But I've noticed now an increasing amount of subjectivity. And, just talking about Planck, for example, I think the demonstration that I've done for you about the existence of Planck, that's clear. It's very simple. But a lot of people think, I don't understand that. It's kind of weird, even though it's very simple, very physical. Simple idea, simple thing to understand, at least in general. There's a lot we need to learn about the quantum. A lot of details we don't know, but at least we know it's there. But some people say, well, that's kind of an opinion that you have. It's not an opinion. What's wrong with this simple demonstration? So then I'll pull out a quote from Einstein, who says basically the same thing. Oh, so if Einstein says it, I said, you don't need Einstein, right? Here it is, it's right in front of you. You should just understand what your senses are telling you in your experience of the world. So an argument, I could have pulled out Einstein at first, right? But an argument based on authority is a weak argument. I could have shown you quotes from Einstein, from Dirac, others about Planck. But I didn't. I don't think that's the way for me to teach you. What did Einstein think about it? What did Dirac think about it? They're very, very smart guys, right? They didn't call it Planck, but they were basically talking about the same thing. There is this physical substance between things that Einstein called space-time. It has nature, it has physical characteristics, it has properties. Now, why do I need to show this? The evidence is right in front of you, right? But it's an interesting thing, and I've noticed it's harder to talk to people today about something like that, even in the physics community. So it's a regrettable trend, but I want to kind of bring it to your attention because I think you'll encounter it when you're talking to other people. It's hard sometimes to get even physics majors, physics professors, talk logically about physics. It's interesting. And it's too bad. We need to try to get rid of that kind of tendency. We need to be able to argue with each other and go at it and find the truth together. When you're seeking the truth together, that's the best way, right? You have to be open to discussion. Okay, so I thought it was been an interesting experience, and actually I'm giving this colloquium now. I've got a schedule. I'm going to be out of town quite a bit this semester and in the spring, because this talk has now stirred up a lot of interest, and I'm getting invitations to go present this talk. And I'm sure everywhere I go, I'm going to get to that point in the talk, and somebody in the audience is going to say, "Oh, no, that's wrong." I hope I do, because I can work with that guy, right, who's going to argue with me and care about it. It's the person who says, "Well, that's his opinion. He's not going to say anything about it. I can't do that." You know, so it'll be interesting to see. It's going to take a lot of work. So anyway, there's a guy from IBM coming in a couple of weeks, and Professor Sardashti has been here. He's bringing this guy in from IBM, and he says, "I want you to talk to him about quantum mechanics." So, you know, there are people who are interested and who will take the time, but it does take time to learn something new. Yes, ma'am.
Okay, so there's also a third type of person, that person that thinks it's your opinion and is dead set that you are wrong and tries to convince you of that. How do you deal with it? Like the kettle math.
Right.
Like how do you just leave it? Because if you can't get through to them, like
you
there's no arguing with stupid. Like
Well,
Someone
I
said
don't think you start off by presuming them to be stupid, right? That's not the way to work. I think you have to have the attitude. There are a couple of ways that will help. One is to have the attitude that they're intelligent, until you find evidence of it. Right? And also that they have goodwill. You don't start off assuming that they have that belief because they have bad will. That's not a good place to start either. So one thing that can help is to listen to what they're saying and express it back to them, because every statement that means something has some truth in it. So you start with their statements and you try to dig out what truth is there. Because then that has a way of disarming you. If you're listening to them and you're trying to find the truth, you're trying to find the common ground you have. Physics is common ground because everybody has an understanding of the physical world. So if you can get back to that, the objective nature of things, and start there. So that means if you can, it's got to be starting off at a low level. And this is something that we're all pretty bad at, actually. We're not really very good at it. So you have to recognize that as well in yourself and myself. It's something that takes work and time. So if you can turn it around so it's not an adversarial thing, if you're both looking together for the truth, then I think you can make some headway. But there are just some barriers you can't overcome, right? No matter how hard you try. And that's why, in fact, I say that the opposite of love is not hate, it's indifference. Because somebody who reacts, "That's wrong," I can deal with that guy. I can tell him, "No, it's not wrong. We'll go over it together." He cares about it. Somebody who just doesn't care, that's harder than somebody who will argue with you. If that person arguing with you is actually after the truth, that's what you got to find. If they care about the truth, then you can work. All right, so let's see. I want to show you falsehead.com. This is on your homework. Just let me, oh, what happened to this now? There we go. Howard Long, why is the perspective? Hello. Oh, mute. There we go. Why don't I? There we go. Okay, how do I get the screen down? I guess I got to turn this off. That's regrettable. Take a couple seconds for it to let me There we go. So this little website, very nice. It has a demonstration of waves in different circumstances. And it's a two-dimensional thing that it's simulating here. It's a simulation, of course. And it has all kinds of things you can change about it. So this is a single source that's emitting a wave, so it's some kind of source that's oscillating. And you have over here a pull-down menu. You can do sound waves or light waves. What's the difference between sound waves and light waves in the simulation? How would that affect the simulation?
Speed.
Now the dispersion. The relationship between the frequency and the wavelength. That's how sound and light are different. Right. Okay, so and microwave. I don't understand. I haven't read enough on this thing. There are a lot of details down at the bottom of the page. What is the difference between microwave and visible light? I don't know how that would be different if the scale is chosen so the wavelength is the same. So I don't quite know that. You can change the source frequency. So now higher frequency, shorter wavelengths. Propagating outward. Pretty cool, huh? Okay, so let's go to plane wave. Here's plane wave. We've done plane waves. We did this in e to the IKX, right? Real and imaginary parts of e to the IKX minus omega. Okay, now you can imagine, say, x is in this direction, and y and z are in this direction. So the wave front is a plane. Planes are propagating downward. That's why they're called plane waves. So to get a plane wave, you could get very far away from the source, and those curved waves are going to be coming flatter and flatter, right? As they get farther away from the source, the radius gets bigger. They're closer and closer to the plane wave. Okay, let's see. So, oh yeah, here, let's do intersecting plane waves. One from the left and one from the top. That's a nice example of constructive interference. And you get these propagating blobs. That's pretty cool. Let's see, there's a whole bunch of them here, and I've played with almost all of these. See, there's a lot of different situations here. So you're going to have some of your homework is just going to be played with this stuff. Here's a half plane. Okay, so we have a wave coming down from the top, and there's an obstacle that's blocking it. And notice, I need a pointer. I don't have a pointer. But notice that the wave, there's wave out here behind the obstacle. That's diffraction. So whenever you have a sharp edge like this, the wave can propagate out behind the obstacle. And that's diffraction. It's different. It's the same thing we were talking about when we had slits before. The diffraction will happen anytime there's a sharp edge. Newton saw this and it talked about diffraction. You can see it happening around the knife edge. See it. You have to get the right circumstances to see this kind of stuff. Again, you can do this in the bathtub. Okay, let's see. Here's another one on obstacle. There's you can see the obstacle. It's got two edges instead of just one edge. And you can see the wave going around the obstacle. Pretty neat, right? So the obstacle doesn't keep the wave from getting in behind it. It does some, because otherwise, without the obstacle, there'd be a lot more intense wave propagating through. But there's a lot of stuff in the shadow of the obstacle. Okay. Let's see. Let's look at a single source. Now these are round waves. They're spherical or circular waves, right? In 3 dimensions, they would be spherical waves propagating out. So those would be spherical rather than plane waves. Right? But as I said, if you get far enough out here, these things are looking flatter and flatter. So they closer and closer to plane wave, farther out you get. Okay, let's put in 2 sources. get an interference pattern. Let's look over here. You can see that there are places here where there's no wave. There's a node. There's a node. This is kind of like what we were seeing with the double slit. In fact, we're going to do the double slit here in just a second. And you can change the source frequency, and that will change the interference pattern. You can see now we've got shorter wavelength. We've got more nodes. Distance between the nodes is shortened. And this pattern will have to do with these two sources. Let's see if I can move the source. I don't think I can. Yes, sir, Mr. Bob.
So basically, like
Look,
the places where you see no wave, it's just like because the two sources are canceling each other out.
That's your homework.
Okay.
Is to see how that works. Okay. We're going to do something like this for homework. Prep you for that. Okay. So you're going to study this pattern over here on the screen. If we had a screen over here, there'd be dark regions and light regions, right? And the separation between those dark regions, the nodes, depends on two things: the wavelength and the separation between the sources, the distance between the sources. So you're going to just play with this for a while just to get a feel for it. Let's see, dipole. Okay, so the dipole, the two sources, instead of in sync, they're alternating like this. Changes the interference pattern a little bit. And here's a quadrupole. No, flatter. Quadrupole has four sources, two in sync and two out of sync with those. Okay, let's look at the, oh yeah, this was pretty cool, beats. Here's beats. Okay, now beats has a, oh, I can't see it, oh man. Down. Here we go. Okay, so there's a probe. You put the probe anywhere, and you can see the signal at the probe. And then you can, and so you can see here that there is, looks like a double slit fraction pattern, right? There's an envelope, and then there's little wiggles in between. So there's two different length scales in this, and you can kind of put it around in different places and see. So, can't change the source frequency now on this one. I'd like to be able to do that. Oh, sonic boom, that's pretty cool. What's a sonic boom?
Break the sound barrier.
Yeah,
That's
the
what makes
source is traveling faster than the speed. The speed of sound. And so you can see it is the waves get pushed up together into a front. The sonic boom is when it goes by. Have you heard of sonic boom? You don't hear them so much anymore. Okay. Well, I grew up in Pensacola, and they were breaking the sound barrier all the time. The pilots were learning how to fly supersonic. Boom all the time. So that's what you get. You get to hear the boom when the cone passes over. Okay. Let's do the single split. Okay, now you can change the source frequency here. So I'm going to go down, way down in frequency. Okay, so that corresponds to a long wavelength. And the diffraction is, the wavelength is much longer than the slit width. And so it's kind of a mush. But if you raise the frequency up so that the wavelength is now comparable to the slit width, now you're getting a cleaner looking diffraction pattern. And you see how the wave goes out all directions from the slit. It's going out even out that way, some of it. Okay, now let's increase the frequency, shorter wavelength. Okay. So there's a sweet spot there to get the diffraction pattern. It's diffracting, but it's not as, this is just more striking when the wavelength of the wave is comparable to the slit width. Now we're going to do two slits. Okay, can you see the two slits? They're kind of small, and they're about, they're like, the distance between them is like 3 times the width of the slit. And of course, you can change the frequency, which means change the wavelength. Okay, now there's this is kind of a mush there, but you get the wavelength of the wave close to that. Here it goes. Close to the slit width and also the distance between them. There's our double slit diffraction pattern.
Can you move where like the slits are?
Oh, no, good question. Oh, you can see the reflection too. Oh, that's cool. I don't seem to be able to alter the separation between the slits or the size of the slits, but there's a write-up at the bottom that I haven't read all of, so there may be a way to do. Oh, what's going on? I'm gonna restart it. Messed it up somehow. Okay, so we're back to there. So you can change the frequency, which it translates into the wavelength, right? Through the dispersion relation. The frequency of the source determines, the frequency is determined by the source. The wavelength is determined by the frequency of the source and the dispersion relation. Yeah, good question.
That's a question. Are you sure the 3D view got changed?
Yeah, I don't like it as much. You might,
Oh,
yeah, it doesn't help me a lot.
I just want to see if it looks.
Yeah, I think there are some things, some ways in which it would be cool. Do you have questions?
Yeah, so for the damping factor, would that like simulate like moving through a medium of some sort?
An absorbing beat. Yeah, so sound wave would be absorbing energy. The air would be absorbing heat from the sound wave, for example, or glass could be heating up. The light would be propagating through it and be heating it up. So I guess that's what damping is. I haven't played with that. Good question. So we really crank up the damping. And the wave is getting weak out away from the slits. Okay, so we're not considering damping in our, they don't have, unfortunately here, this Schrodinger equation. It's not one of the choices here. They have waves, sound waves, visible light. I wish they had Schrodinger equation. That's what I'd like to see. Because it's different. It's got a different dispersion relation. And these things are going to be different for the Schrodinger equation. Okay, so you get the basic idea. You're going to mathematically explore the nature of this double slit diffraction pattern. We talked about that in chapter 1, about how important the double slit experiment is for electrons, right? Passing electrons. So this would be something like this for the wave function. For an electron beam coming in through two slits, the de Broglie wavelength has to be comparable to the width size, the slit size and the distance between the slits. They all have to be about the same. You have to have the energy of the electron, the momentum of the electron has to be just so that it matches the wavelength, the de Broglie wavelength for the electron, matches the slit width. And this is the wave function, right? Remember, it's probability amplitude. The guiding wave is going through both slits, but the electron only goes through one. But you collect out here, run a bunch of electrons through, you collect a histogram, you see very few electrons here, a peak here, few electrons, a big peak here. That's the double slit diffraction pattern. Okay, and there's more detail in that. Okay, so let me help you get started on that. Okay, the first thing is we want to be able to have just a single source with spherical waves coming out. We've talked about plane waves, and remember we solved the time-independent Schrodinger equation. In one dimension, like this, that gives rise to solutions of this form, where K is related to the energy, meaning the wave number is related to the energy this way. So if I could have a plane wave solution, which looks like some of the plane waves that you saw illustrated, simple plane wave, just one by itself. Okay, but this is not like that, right? This has curved fronts. So this can, Dr. Rizzi's written down the time independent Schrodinger equation in 3 dimensions. In terms of the Laplacian. The Laplacian is like the curvature in 3 dimensions. Some of the curvatures in each direction. So this is in Cartesian coordinates. So this would be we could solve this equation. That's not very convenient though, because you have something which is spherically symmetrical, so it's not convenient to use Cartesian coordinates, which Cartesian coordinates are much better suited, for example, to plane waves than to a spherical. So what we want to do then is to look at in terms of spherical coordinates. So the spherical coordinates involve distance r from the origin. So you have an origin. That's true for the spherical coordinate system like it is for Cartesian coordinates. But you also have 2 angles. To specify a point on the surface, you need latitude and longitude on the surface of the sphere. So you need 2 angles. The angle from, pick out the z-axis to be special. Let me get rid of these spherical wavefronts. Let me draw the coordinate system I'm going to use to describe it. What we want to conform to the shape of the wavefront, so we're going to use spherical coordinates to do that because it's spherically shaped wavefronts. Okay, so there's 2 angles. We're going to study the spherical coordinate system more when we get to the hydrogen atom, because the spherical coordinates are much better for treating systems with spherical symmetry like a hydrogen. Okay, so don't worry about the details of the angles. There's 3 coordinates, distance from the origin, and the 2 angles that correspond to longitude and latitude. Don't worry about the details of the angles. That spherical wave doesn't depend on the angles, right? So we're looking for a solution that depends only on r. And when we have a function that depends only on r, the Laplacian acting on that, a little more complicated than the Cartesian version of it. So the Laplacian also has terms, usually also has terms involving the angles, but this wavefront that we're talking about coming out from the source is spherically symmetric. So we only need to deal with the r dependence of the wave function. Okay, so that means that the wave function, the solution of the Schrodinger equation, where psi depends on r, this is the Schrodinger equation in 3 dimensions, where the wave function depends only on the distance, not on the angle. Spherically symmetric, propagating out from the source. See how I got there? There's a part about the Laplacian. This might be new to you. some differential operator, second order differential operator. Second derivative, two derivatives in R, but we got these powers of R.
So it's a derivative inside of a derivative.
Yeah,
Ew.
yeah, you take the derivative, multiply by R squared, take another derivative, divide by R squared. That's the Laplacian spherical coordinates with respect to R. Yes,
The Laplacian is the upside down triangle.
triangle.
Is that the same as the gradient or?
It's the square of the gradient. The Laplacian is the divergence of the gradient. Remember in the NF, the divergence and the gradient. The divergence of the gradient is the Laplacian. That helps you. So the Laplacian is the divergence of the gradient. Whatever the coordinate system you use, divergence and gradient are going to have different form.
Apparently here.
There's a private airport near, roller coaster road.
Yeah, the house there.
Yeah, that's down in the low country.
So it's pretty fast.
Yeah, he's going fast. Okay, yeah, I did hear boom. Okay, you're going to demonstrate. I'm going to give you the solution for this. This is the solution in 3 dimensions. So this is the spherical analog to the plane wave that you had before. It looks very much like it, except we have an R here, and we're dividing by R. So this is called a spherical wave. And K has the same relation to E that it did in plane wave. And the full solution, the time, this is a pure mode, the full time-dependent solution. The I KR over R times E to the minus I omega T. We can combine the exponential. Like this. And so this is an outward traveling wave. There's another one that's traveling inward where you flip the sign of A here. That would be an inward traveling. It's easier to imagine an outward wave because you have a source at the center coming out. It's kind of harder to imagine how you could get an inward wave. Spherically symmetric coming in, right? But it's a solution to the Schrodinger equation. Okay, so now that we have that, try to go tackle the problem, not the slits, but the double source. So to do the slit is actually pretty hard, but you're going to consider that there's 2 sources lined up like this, each emitting an outward going spherical wave. You're going to look at the result. Okay, so we're going to have a superposition of 2 waves. One is the outward wave coming from this source. The other is an outward wave coming from this source. So the wave function here is going to be the sum. Let's just, the frequency is very simple. Everybody has the same frequency. So we're just going to look at the spatial part. Where R1 is the distance from the first source and R2 is the distance from the second source. So that distance is different. The distance from here to here is different than the distance from here to here. And so those complex numbers are going to be different. And how those 2 numbers relate to each other, of course, depends on, say, the angle here from some of this point here. Okay, so there should be enough hint in the homework to get you through. You're going to make some approximations because this form is already actually a little too not very tidy for a first time at it. Homework problem. Yes, sir.
So is it like through like these derivations where you get the equations like for the double slit and like the simple or relatively simple relation compared to all this?
Say that again?
So like I can't remember the exact equation for it, but it's the equation we have for like double slits where you can predict like the wavelength of the slit width.
Yeah.
Like where they're all correlated.
Yeah.
Does that arrive from like derivations like this?
Yes, that's right. Yeah, we're not at, so our slits don't even have any width to them, right? They're really narrow, but the distance between them is still there. So we still have that. But to do the real full slit problem, we have to consider how to solve the Schrodinger equation with slits. And so we have a plane wave coming in. And then what we want to find is this solution outside here. This is an approximation to the full solution. And so to do this problem right, I would start with the Schrodinger equation and apply certain boundary conditions to the wave function. Namely that the wave function vanishes on this piece here on the top, and then solve it downstream. Scattering problem in 3 dimensions.
Yeah. So you want to say like the potential, like that potential thing that's used for.
Yeah, you could use that, right? You could have, say, if the potential is infinite here, here, and here. It's not a bound state problem, it's a scattering problem. You got something coming in, there's going to be some reflected part and some transmitted part. That's a pretty hard problem. It was taking a little while to do a good solution. This is a pretty good approximation to the solution. And that's what you're going to do is to make, even this is already a little messy, you're going to make some approximations even to this. And then you're going to evaluate the wave function over here on the screen. Find psi of x along the screen, and then square it to get the probability. So you have a beam of electrons coming in, and with really narrow slits. You're going to find the diffraction pattern on the screen. So you're going to see something like this, some kind of pattern. This corresponds to no electrons, and there's some electrons are bunched up in these regions where the maximum probability. So you're going back to look at the double slit problem. Now that we know a little bit about the Schrodinger equation, we can use what little bit we know to go back and look at the double slit experiment. Okay. All right. See you Monday.